December 1938. Inside a quiet laboratory in Berlin, chemists Otto and Fritz Strassman were running a new experiment. They were firing neutrons, small subatomic particles, directly at a sample of uranium. They expected the uranium nucleus to merely chip. Instead, the nucleus absorbed the impact, shuddered, and fractured entirely in two. Reviewing the data from exile, their colleague, physicist Lise Meitner, recognized what had actually happened. She identified the process as fission. The atom had split, and in doing so, it released a burst of energy. The energy released by a single splitting atom is incredibly small, but Meitner and her contemporaries noticed a mathematical detail in the process. When that uranium nucleus broke apart, it also threw off extra free neutrons. These freed neutrons slam into neighboring uranium atoms, causing them to split and release even more neutrons. 1 becomes 2, then 4, then 8. In fractions of a microsecond, the chain reaction multiplies exponentially, releasing a massive, self-sustaining wave of kinetic energy. This physical breakthrough arrived exactly as Europe was plunging into global war. The theoretical math suggested a superweapon was possible, creating an immediate race to build one before Nazi Germany could. The fear of a German bomb launched the United States into the Manhattan Project. This was a sprawling, top-secret empire constructed rapidly across the American landscape, eventually employing over 130,000 people. Driving this massive apparatus required a unique partnership. General Leslie Groves enforced strict military logistics, while theoretical physicist J. Robert Oppenheimer managed the project's complex scientific problem-solving. The challenge required inventing the physical mechanics necessary to enrich raw uranium and breed plutonium on an industrial scale, a feat of engineering humanity had never attempted. On July 16, 1945, in the New Mexico desert, years of hypothesis and engineering converged. The Trinity test turned the mathematics of fission into a blinding physical reality. Weeks later, in August 1945, the military deployed 2 atomic weapons over the Japanese cities of Hiroshima and Nagasaki. The official government rationale stated the strikes were necessary to force a swift surrender and avoid a massive ground invasion. The result on the ground was immediate, massive annihilation. The blasts vaporized the centers of both cities in an instant. The initial explosions and the subsequent radiation killed well over 100,000 people. Human ingenuity had proven it could split the atom, but its first act with that discovery was absolute destruction. The American monopoly on atomic weaponry was incredibly brief. In 1949, the Soviet Union successfully detonated their own fission weapon, ending the American monopoly and dividing the world into 2 nuclear-armed camps. This chart tracks the resulting Cold War arms race. You can see the stockpiles of both the United States and the Soviet Union climbing rapidly from near zero, eventually reaching a global peak of over 70,000 nuclear warheads. To manage this power, a new doctrine emerged: mutually assured destruction, or MAD. If both nations can completely annihilate the other, pulling the trigger guarantees your own destruction, keeping both locked in a standoff. This standoff took a heavy psychological toll on the public. An entire generation of schoolchildren was taught to practice duck-and-cover drills, hiding under their wooden desks to survive blasts capable of vaporizing steel. Global peace was no longer maintained by diplomatic trust, but by the shared, omnipresent threat of planetary extinction. Today, the strict 2-player standoff of the Cold War has dissolved into a much more complex, multipolar landscape. The total global stockpile has actually decreased to roughly 12,100 warheads. However, the physical danger of those weapons has spread. 9 nations hold today's arsenals: the US, Russia, China, France, the UK, Pakistan, India, Israel, and North Korea. Conversely, vast regions, Latin America, Africa, Southeast Asia, Central Asia, and the South Pacific, have formed nuclear weapon-free zones, legally committing to a future without the bomb. The modern geopolitical dynamic is a constant tug-of-war between a small handful of nuclear-armed states and a massive non-nuclear majority. The paradox of fission remains a permanent fixture of human existence. The exact same subatomic physics that vaporized cities is also used to sustain civilian power grids. Modern nuclear reactors generate vast amounts of stable, carbon-free energy. This technology offers a highly effective tool for combating the modern threat of climate change. We cannot reverse the process or unlearn the secret of the atom. We can only choose how we capture and channel the energy it releases. The knowledge discovered in 1938 cannot be unlearned. Because the secret of fission is now a permanent part of our reality, humanity's survival relies entirely on the collective intelligence of the non-nuclear majority and international diplomacy.